Probably this one.
It's okay.
Yeah, thank you. So today we will continue our lecture. And now I will show my slide. You see the slide here?
Yes, Prof.
Okay.
Very clear.
Okay. Selamat pagi, everybody.
Selamat pagi, Prof. Selamat pagi, Prof.
Sawadika. Okay, so today continue to our course computational chemistry, and I will talk about the ab initio quantum chemistry methods following our already 3 lectures. And yes, today is here, and tomorrow, next week we will still in the same core of the ab initio. Okay, today we will understand a little bit about our method. This slide is already you have seen for some times earlier, but I like to mention to you about the length of our system. Still very atomistic level. Atomistic means we consider just about 10 to 20 atoms, and if we like to have the accurate method, okay. And for today, we will focus on ab initio. Actually, these are method level of theory and methods, okay, are in the ab initio. That means, we will do everything perfect. And the best one is to start about the Hartree fork over here, Hartree fork. And next week, we will consider about the post-Hartree fork method, including the MP method, CISD, or CC, Cluster cluster, for example. Okay, this is the thing that I would like to focus for you today. So the expected learning outcome for today is that you will remind about the basic concept from quantum mechanics, which quantum mechanics focus on how to solve the Schrödinger equation in order to get the precise results. Okay, and in order to solve the Schrödinger equation, we have the approximation. Last week you have heard about the Born-Oppenheimer approximation and also the LCAO-MO approximations. That means these approximation bring to the construction of basis set. Okay, so last week you have already learned about what is the basis set and how about the basis functions that used in quantum chemical calculations. Okay, so please remind a little bit about the basis set. And today for the ab initio, we still also apply the Born-Oppenheimer approximation. Okay, and you will see that it will apply to the Schrödinger equation based on the Hartree-Fock operator and the wave function. Okay, and then in order to solve the Schrödinger equation, we need not only the wave function, but also the numerical analysis or numerical method that we need to solve the self-SCF. Okay, so we will learn about the idea how to get the wave function, and then we can solve the Schrödinger equation. At the end, you will understand about the Hartree-Fock method and related techniques. Okay, and also at the end of this lecture, you will see about the strength and weakness of the method and some applications. And I like to tell you that every method that we learn about computational chemistry, they are good, but there are some limitations. Okay, not everything that can be solved Schrödinger perfectly. Now, come to the inspiration in science. This picture shows you about a very important scientist behind the foundation of quantum mechanical ab initio and also the density functional method that we are going to learn in this course. Here is Professor Heisenberg. You may know about his finding about the uncertainty principle, especially the properties of the electrons, okay? And he got the Nobel Prize in Physics, 1932. And based on the Heisenberg, this can bring to the very efficient and very important issue to solve the Schrödinger equation, okay? So you may see the face of this Professor Schrödinger. He is an Austrian, okay? And he proposed a very important equation that is the heart of quantum mechanics, that is Schrödinger equation, okay? And he obtained Nobel Prize in Physics in 1933. We need to mention about this gentleman, Slater, who proposed the Slater Determinant. And for the Slater Determinant, it brings to the wave function. And the wave function, it is the equation that explain about the motion and the properties of electrons, okay? So Slater Determinant is very famous and very useful, and it is indeed the foundation of wave function. And also when we deal with the many electron system, it is not easy, okay, to solve the many electron system. Not only Slater Determinant that help to solve the Schrödinger equation, but also later on, Hartree and Fock proposed how to solve the Schrödinger equation in the mathematical ways and apply to the Rotan-Hall equation. Okay, so Professor Hartree and Professor Fock are also really indeed important person. And followed by the development in post-Hartree-Fock, which is the density functional theory. The concept of density functional theory we will learn in the next 2 or 3 lectures, okay? And very efficient method up to now. And Professor Popo and Professor Kohn also obtained the Nobel Prize in Chemistry the same year. And these are the person who are the foundation of quantum mechanical ab initio that I would like to introduce to you. And just remind you a little bit, yesterday, the Swedish Royal Academy of Science announced the Nobel Prize in Chemistry. Very exciting. There are 2 Nobel Prize winners, okay? And one of them is Professor David Macmillan, okay? I also met him sometimes in Thailand in the conference, and very congratulations to him. And also he shared another half of the another half is, may I have a look a little bit? Need to congratulate to both, okay? Professor Benjamin List and David Macmillan, okay, for the development of the asymmetric organocatalyst, right? So very happy about the announcement, and congratulations for both Nobel Prize laureate for this year. Okay, so now we come to the basic concept from quantum mechanics, which I already introduced to you sometime earlier, right? Von Oppenheimer and many electron wave function that we use the term of Slater determinants, okay? And later on with the LCAO-MO approximation, we introduce the basis set. Now, we are considering the ab initio method. Some of you might hear about this term ab initio, which actually the ab initio means starting from beginning. Okay, and sometimes we call it first principle calculations. That means ab initio calculation. That means we start from the beginning. That means we include everything, the base. Okay, and I would like to say that it is the core quantum chemical method, quantum chemical calculation method. And in computational chemistry, it is the main method that we try to solve our system at best, but sometimes it's not easy. Okay, and then we will start from the Schrödinger equation, which we consider the time independent Schrödinger equation. We cannot include the time dependent due to the very complicated. Okay, and based on the Born-Oppenheimer approximation, we obtain the time independent Schrödinger equation where the Hamiltonian operator include the variables from electrons only. And in the case of the nuclei coordinates, it will come back later on as one parameters or some parameters. Okay, so from the time dependent Schrödinger equation, which present in the left, we consider to be the equation that very famous, H psi equal E psi. And as you may know that the psi is the wave function of the system. Recall you to the basis set last week. The basis set include the mathematical functions that explain the motion of the electron, okay, or the particle, okay, and the H is the operator, mathematical operator. And the eigenvalue equation is that when the operator operates on the wave function, it will result the value, we call it eigenvalue. In this term, it is the E or the energy eigenvalue and multiply with the wave function. This is very uniqueness of the eigenvalue equation. Okay, so this is the value, eigenvalue, which is the energy of the system. So Schrödinger equation is that we try to solve the system, the molecules, our molecular system, our molecules, our electronic system, and obtain the energy. Okay, this is the core, the heart of the Schrödinger equation, that we would like to get the energy term, the value of this eigen. Okay, and for the operator, which we call it Hamiltonian operator or H, it consists of the term that represent the electronic Hamiltonian operator, okay, which only electron motion. And I would like to remind you about the time independent Schrödinger equation, which we try to solve this equation H psi equal to E psi, and the H, as I said earlier, it is the Hamiltonian operator, which can represent by the sum of the kinetic energy term and potential energy term. Okay, so whenever it operate on the wave function, it results the energy of the system. Sometimes in some book, it write the Hamiltonian operator like kinetic energy term plus potential energy term. And for the many electron system, which probably some atoms or some molecules. The Hamiltonian operator will be expressed in the following 5 terms. Okay, the first term represents the nuclei kinetic energy. Okay, donated as shown in this slide, you can see a little bit minus h bar square by 2 and summation of 1 over m alpha, and this is the Laplacian operator, means the coordinate of the particle or the electron. Okay, and m alpha is the mass of the particle. Okay, and h bar is the Planck constant. And the second term also electronic kinetic energy term. This is the nuclei kinetic energy, and this is the electronic kinetic energy term. This is the kinetic energy term overall. Okay, we denote by the T hat, and sometimes in short, we use this notation to be minus h bar over 2m and d square by dx square. And another 3 term represent the potential energy term. And the potential energy term will consider the nuclear repulsion. If you remember, the nuclear repulsion represented by the charge of the nuclei, which is the Ze. Okay, one Ze and another Ze. So you can obtain the Z alpha E, Z beta E, and then you can have the Z alpha Z beta E square divided by the distance between the 2 nuclei, alpha and beta. And the next term is the nuclear and electron attraction. So imagine if you have the nuclei, okay, the nuclei Z alpha E and interact with 1 electron. So you have the charge E. Then this nuclear electron attraction resulting in the Ze square over the distance between the nuclei alpha and the electron I. Okay, and the final term is the electron repulsion, with the charge of electron is E, okay, and E multiplied by E, so you can have the E square and divided by the distance between the 2 electrons. We call it electron I and J. Okay, so this formula is really famous, and you can try to understand this physical meaning first. Okay, imagine you have 1 nuclei and 2 electrons. So this is the Laplacian operator, which represents the Cartesian coordinate. Okay, and it can be, in short, use the Laplacian operator notation. So that we consider about the Hartree-Fock operator. So Hamiltonian operator. Now, Born-Oppenheimer approximation also apply to the wave function. And the wave function of the many electron system is the function of electron and nuclear coordinates. Imagine that you have the nuclei and electron, okay? And then you have the coordinate of the nuclei and the electron. So in this case, we can have the wave function, which depend on the coordinate of the nuclei and depend on the coordinate of the electron, which we represent by the big R for nuclei and the small r for electron. And the R is the nuclei coordinates, and small r represent the electron coordinates. So you can imagine a little bit, right? that you have nuclei, one nuclei and one electron. And so you have to coordinate. But the electron and the nuclei still moving. Okay, especially electron is moving all the time. It's very small. So the motion of the electron and the nuclei are actually moved together. Okay, but due to the mass of the nuclei, which is much heavier than the electrons of about 1,800 times over the mass of the electron. That means the nuclei move slower than the electron. If you can imagine the kinetic energy of the electron from the equation 1/2 mv squared, for example. So the feeling is that like the nuclei is just fixed at one station and the electron rotate or moving around the nuclei and very, very fast. And in this case, Born-Oppenheimer approximation has been applied to the wave function. And to the high degree of accuracy, the electron and the nuclear motion can be separated. That means the wave function, which we start by psi r, big R and small r, can be separated to be the wave function of the electron and the wave function of the nuclei. Okay. So now Born-Oppenheimer approximation has been applied to both Hamiltonian operator and the wave function. And then in order to make this possible, we consider to solve the Schrödinger equation only the electronic part, only the wave function that depend on electron motion. And so we can sometimes consider that we solve the electronic Schrödinger equation. Now, we can solve the electronic part of the Schrödinger equation separately. By consider this equation, we can have the Schrödinger equation in terms H electronic and wave function electronic equal to eigenvalue depend on electronics and multiply by the wave function, electronic wave function. Okay, so based on this, we can introduce the Hamiltonian operator to be the Hamiltonian operator that depend on the electronic part. Okay, so you can see that this is the very famous electronic Hamiltonian operator, right? And based on the Born-Oppenheimer approximation, it is also very important to mention about the potential energy surface, okay, or the PES. Potential energy surface obtained from, this is the UR potential energy surface of the electronic energy and the potential energy of the nuclear repulsion. And the VNN stand for the charge interaction or nuclear interaction, if you remember. Okay, so we have the summation, double summation of the set alpha set beta E square divided by the distance between the two nuclei. And this term is very important. We can consider an example of the two nuclei, which is the mercury and bromide, mercury bromide. Okay, these are the two atoms, the diatomic interaction. So we can consider the potential energy surface of these two nuclei. You can see from this graph, and the x-axis represent the distance between the two atomic nuclei. Okay, and this is the potential energy potential energy curve that you can see that the equilibrium distance between the mercury and bromine is somehow about 4.6 or 7 atomic unit. I have to mention about the atomic unit of the length, which come from the equation that one Bohr or one atomic unit equal to 0.529177 angstrom. Okay, let's say half angstrom. So the equilibrium distance between the mercury and bromine is about 4.6 or 7 atomic unit. Or if you say half, it's about 2 atomic unit, 2 angstrom. Okay, and if you can go further to longer length, so you can see that the energy that make the two atoms far away, you need somehow the minus 16 kcal per mole. Okay, from this you have to make it separated far away. Okay, and dissociation energy will be here about minus 16. So these are the important of potential energy of the diatomic potential energy surface, which is very famous and quite important. But we can also consider the potential energy surface, or the PES, which bring to solve the nuclear Schrodinger equation. We have electronic Schrodinger equation, and then we have nuclear Schrodinger equation, which we can apply the Hamiltonian operator of the nuclei and the wave function of the nucleus. Okay, and then we obtain the equal to eigenvalue of the nucleus and the wave function of the nucleus. So we can have the Hamiltonian operator of the nuclei motion. Yeah. So if we can solve the nuclear Schrodinger equation, that means we can determine a large variety of molecular properties, like mercury bromide. Okay, and one example of the potential energy surface application is that we can introduce the vibrational energy levels. For example, you can see from this slide, we have the hydrogen fluoride, and we have the potential energy curve of the hydrogen fluoride, and you can see that this can represent the vibrational mode of the energy level of the hydrogen fluoride, right? So there are so many examples that we can learn if you are interested in. And another application of the potential energy surface, when we consider the polyatomic interactions. For example, in this case, we have atomic oxygen and hydrochloride. Okay, and you can see that when the reaction occurs, it produces the OH and the atomic chloride. So if we consider how can this mechanism occur, in reality, in the experimental, probably we cannot propose anything, but from the computational calculations, we can propose based on the potential energy surface of the system. Okay, let's look at this picture. We have the OH, oxygen atom, hydrogen, and chlorine. So it can be possible to go two directions. The first one is that it can come in this direction and separate oxygen, and then you can have the HCl. Okay, and another one is that you can have this direction, right? The reaction coordinate occur, and from the calculations we plot the theta, that means the angle between the HO and Cl. Okay, this is the angle. And then we can also plot the reaction coordinate, the distance between the O and H. And we generate the coordinate of the system in many ways. And then we can solve the potential energy nuclear Schrödinger equation and obtain the energy. And finally, we plot on the three-dimensional or the reaction coordinate like this potential energy surface. And you can see that there are two paths. Okay, and when we plot about the equilibrium constant, okay, and the 1/T, we can have the potential energy surface to compare with the experiment. Okay, and the dot over here, the black dot, you can see that it is the point from the experiment. And the proposed of the potential energy surface 1 and also potential energy surface 2 can be possible, right? So this one is quite nice, and you can imagine about the new electronic Schrödinger equation. We obtain the energy, and then we also have the nuclear Schrödinger equation. We can also obtain the potential energy surface, okay, of the many electron or many atomic system. Okay, and this is very important and quite famous and useful for many organic chemical reaction in order to explain what happened in the experimental work. So now let me bring you to a little bit more about how to solve electronic Schrödinger equation, which is the main part of the computational chemistry. This is very challenging and not easy, actually, quite complicated. We consider the systems which involving more than one electron. Okay. Keep in mind, if you have one electron, you can exactly solve the Schrödinger and correct the data as compared to the experiment. But when we have two electrons or more than two electrons, it's still impossible to solve exactly. And why? When you consider the Hamiltonian operator, which including the kinetic energy of the electron, which consists of these two terms, and the electron-electron interaction. Okay, this part is really very hard to solve because the electron, it moves in all directions very fast. Okay, so we cannot solve based on only the Cartesian coordinate, but we have to make it to be overall space. And we need the integral term and differential term and many terms to solve exactly the electron-electron interactions. So this is the big problem and challenging for computational chemistry methods. However, we need further approximation and we need development of the method. Many methods try to solve the electronic Schrödinger equation. Okay, and even right now is still ongoing to improve the efficiency of the method that available. Okay, as I told you sometime earlier, it depends on how many atoms It depends on how many electrons. It depends on how many terms, Slater term determinant, and very big matrix determinant. Okay, and can we have the mathematic procedure to solve this kind of integrals? Okay, so very challenging. We will consider this later on. Let's look the approximation on the wave function. As I said, the wave function is the heart of Schrödinger equation because it consists of the motion of electron. It consists of the properties of the electron in the space, in the molecules. Okay. So after we apply Born-Oppenheimer approximation, the next important approximation is the expansion of the wave function in the basis of Slater determinants. You remember about the linear combination of atomic orbital to construct the molecular orbital. Okay, if we have not so much term or atom, we can solve quite exactly the wave function. But if we have so many electrons in the molecules, we need to generate the mathematical terms for basis function. And this way, Slater determinant is helpful to construct the wave function of the system. So let's see the psi EL, that means the wave function of electron, which stand for the summation of the small wave function. Okay, so we can have wave function that we stand for phi 0, phi 1, and phi 2. Okay, we cannot solve it, but Slater determinant can propose that for the wave function phi 0 is equal to the normalization term over here, 1 over square root n factorial. Okay, and the Slater determinant in this picture, you can see that it consists of the wave function psi 1 and alpha 1. This stands for the wave function of electron 1 in the bracket. Okay, and also it contributes to the spin orbital up alpha and down beta. Okay, so we can consider electron number 2 that it occupy in the orbital 2 and also the spin up and spin down. So you can see that, imagine that this Slater determinant can be big if we have so many electrons. So alpha and beta stand for the spin functions. You remember that the electron can have the spin up or spin down. Okay, there are two possibilities. And the phi 1 are special function or molecular orbitals. Therefore, phi I alpha and phi I beta, we call it spin orbitals. Okay, that means the wave function that represent electron with spin and the orbitals of the molecular orbitals. So in this way, Slater determinant is very efficient and can provide the proper anti-symmetry. Okay, anti-symmetry, that means the electron follow the Pauli principle. That means one electron and the two electrons try to escape from each other. But if both have to be in the same orbital, it should be a spin up and another one spin down. Okay, and the properties of the wave function can be like this only when it consists of the property that called anti-symmetry. Okay, I just remind you a little bit about the foundation of the quantum fundamental of quantum chemistry a little bit. Yeah. So I like to say that right now it's not easy. Our life is not easy. After consider the wave function, after the consider the determinant, Slater determinant, we can go to the next approximation, which we call it Hartree approximation. For example, the Slater determinants can be configurations, right? And if we consider some example like neon, okay, neon is the element in the periodic table. You remember that, the neon, and it consists of the electron of about 10 electron for neon. So the ground state electron configuration, how to stand for, you remember that we learned this since the chemistry foundation of chemistry, probably 101, the very classic course. You have 10 electrons. So the 10 electrons try to occupy in the 1s orbital, okay, 2 electron in the 1s orbital, 2 electron in the 2s orbital, and the rest 6 electron occupy in the 2p orbital, okay. And this would be the ground state electron configuration, or we call it big phi. This is the big phi and subscript 0. That means ground state electron. Okay, so can we consider in other ways? For example, if one electron in the p orbital go out to, or the mobility to 3s orbital like this, so we have 1s orbital, 2s orbital, 2p5 electron, and another one electron can go to the 3s orbital. Okay, and this kind of electron is very active. It's kind of valence electron, and it's very active, and it quite easy to go away, okay, or to make a chemical bonding with other atom or other molecules, okay. So in this case, we can have also the molecular orbital or the wave function that represent this kind of electron, right? So if you imagine, can we have the complete set of the wave functions, okay, that represent all possibility of the electrons that can be occur, okay? But in reality, it's not easy. It's not feasible. We can do it just for some, but not all, right? So next, the Hartree approximation is applied to solve Schrödinger equation, but based on using only one determinant. For example, the ground state electron configuration only. Okay. In this way, we need to apply the variational method. The variational method. Yeah. This kind of variational method, I will talk a little bit later. We consider the energy for the approximate wave function will always be higher than the energy of the true wave function, right? And later on, the variational method will use the self-consistent field SCF procedure. Try to make the iteration, try to make the prediction from the energy of the early of the approximate wave function to predict the true wave function. Sometimes it make many cycles try to predict the new wave function until, right, find the optimal set of molecular orbital for a ground state wave function. And in this way, we can consider that the electron only see the average repulsion of the remaining electrons. Okay, that means if you have one nuclei and many electrons around the nuclei, when we try to solve the self-consistent field procedure, we solve one electron wave function based on other average repulsion from the remaining electrons, right? So this is the way that Hartree approximation have been applied. I think we can see a little bit more on the Slater determinant term. When we propose Slater determinant, you can see that the wave function of the ground state can be proposed, right? And including the spin orbital, including spatial molecular orbital, and including everything. But the key that I would like to emphasize at this stage is that it depends only one Slater determinant. It depends only one Slater determinant. It depends only the ground state electron configuration. So imagine that Hartree can apply for the ground state, but in reality, in chemical reaction, sometimes electron can be on the excited state. So that is another point of view, another technique that we need to find other ways, right? That means for Hartree approximation, it's good, but still some limitation. That's why if you look at the slide that I introduced to you at the very early slide, like this here, the Hartree can put at the very ground state. Okay, very ground state of ab initio. And if you like to consider the excited state of the electron, something like this, or the system that consists of atomic charge or something, so Hartree cannot involve. Okay, so we need to consider the post Hartree. That means other methods have to be developed. Okay, so I think we can we can stop the first part over here a little bit. Otherwise, the student, the audience, may be hard a little bit. After this will be a little bit more complicated.
Okay, so Prof, I think we can give the time to the audience to
yes.
read again and look deeper about the Hartree, especially in ab initio method. I see a question in the chat box. Do you want to take a break first, or we can move to the question?
I think we can take a break a little bit, and then we can come back. Yeah. Okay. And some students can pose their question.
Okay, sure.
Is it okay?
It's okay.
Yeah, so thank you very much.
Have a break for everyone, and also for Supa, thank you very much for the explanations. So for the audience, if you have any questions regarding the lecture, please put in the chat, and we will come back in some minutes, maybe 5 minutes, or more than around 5 minutes. Okay, thank you, Prof.
Okay, thank you. Just post the question if you have. Today is not so enjoyable. I mean, there are so many mathematical equation and concept that we need to understand. But for the student, I know that most of the students that attend this class are the undergraduate student. Okay, so for the Hartree, some kind of the details, it would be good if you go to the graduate course, yeah, and then we can go into more details. So in this course, I think I can introduce some concept, okay? And if you like to go into details, that no problem, yeah? There are so many things that we can learn later on in details, if you like. Okay, so see you a little bit. 5 minutes break. Thank you.
Thank you, Prof.
Okay, sorry. Yeah, I come back.
Okay, welcome back, Prof.
Yes, and from the question, Mentary, right? Mentary Putri asks about the big R and small r in the Born-Oppenheimer approximation. So it's very easy to understand that due to the big R mean nuclei, the coordinate of the nuclei, and the small r is the coordinate of the electron, right? So I hope that you may remember the slide here. Yeah. After the lecture, I will send the PDF file of my PowerPoint to Mita. So then you can share to the student. So now here, yeah, big R mean the nuclei, the wave function. You imagine you have one nuclei and one electron. Nuclei is 1,800 times heavier than electron. So nuclei like standing. And electron just move around because it's so small and it's move very fast. Okay, like elephant and the fly. Actually, the nuclei also move, okay, but it moves very slow as compared to electron. So in this case, Born-Oppenheimer approximation can apply to the wave function, and we can separate the wave function, which is actually include the nuclei coordinate and the electron coordinate. We can separate to be two wave function, and they multiply, okay? Wave function, electronic wave function, and nuclei wave function. And then later on, we can easily solve only the electronic Schrödinger equation. And you can see that H per psi equal E per psi. You have only the wave function that represent electron, right? In this way. And also you can have nuclear wave function. I hope this a little bit help to the student. Huh?
Thank you, Prof.
Yes. So now we will go a little bit to understand. Yeah, I talk about the approximation, Hamiltonian and wave function, and the ground state wave function in the Hartree fog. Now we come to the equation to solve in ab initio theory. H per psi equal to E per psi. This is only one equation that used in all computational calculations, including ab initio, semi-empirical, that we are going to learn, and also the density functional theory. Okay. The objective is to solve this equation. And for the Hamiltonian operator, we know it exactly. Okay, we know it exactly what the terms are. If you remember, just count nuclear repulsion, electron nuclear repulsion, and the kinetic energy of the nuclear or the kinetic energy of the electron. We count every interaction like this. And also the psi. The psi is the total electronic wave function. But this is not easy. So we have Slater determinant to construct the wave function. And then we have Born-Oppenheimer approximation. But in practice, we need to approximate it based on variation of the wave function. The first trial wave function and solve the equation, and then get the coefficient to predict the new wave function. and try to do this like iteration many times until we reach the criteria that we can accept. Okay. So each term, the total electronic wave function will have 3 n spatial variables and n spin variables. And n, big N here is the number of electrons. Okay, so we have 3 n spatial variables and n spin variables, resulting in we have the total 4 n. Okay, when n is the number of electrons. So you can imagine, just understand the concept, yeah? Solve this equation and try to find the exact Hamiltonian operator, try to find the very acceptable wave function. And if so, we can solve operator operate on the wave function, then get the eigenvalue or the energy of the system. That's it. This is a ab initio, right? So now I like to come to the Hartree-Fock method. The Hartree-Fock method will generate the wave function, okay, and later try to find the eigenvalue on the wave function, okay. For the notation over here, it is mathematics, okay, and many terms. Don't worry, just give you a little bit feeling that in ab initio we need to deal with several mathematical terms, okay. We deal with the matrix, we deal with the many functions, okay. In reality, we cannot solve by ourselves, but numerical methods and computational calculation can help to solve, to get the best wave function for us. When you get the wave function, at the end, you will get the energy. That's it. It's a very easy concept, very easy, okay? But practice is not easy, right? So you can see some notation of the Schrödinger equation. Sometimes we represent in this symbol, yeah? Bracket, wave function, Hartree-Fock, and operation, H hat, and also the wave function Hartree-Fock. Actually, it is the integral term, yeah? And if we can solve this integral term, then we can get the eigenvalue, okay? And the eigenvalue over here is the energy of the nuclei, and also some mathematical term that represent the interactions, okay, between the two electron integral over here. MKNL, that means they represent the electron in the orbital. But at the end, as I said, finally, we try to get the difference between before the trial and the final trial, to get the differentiate of the electron between the initial state and the final state to be zero, I mean consistent, okay? And if so, we can solve the Schrödinger equation. Therefore, in order to do this step, as I explained to you, we call it the Hartree-Fock equation or the Hartree-Fock method. Yeah. So the physical meaning of all these things, I can introduce to you that for the Hartree-Fock method, it is the method that deals only one single determinant. Remember that? Remember the big file over here, the ground state orbital, okay, the ground state orbital. the wave function of the ground state. Okay. And when we give the approximate wave function, or psi, I mean that we need not to get the real wave function, just approximate, just some function, okay? And then we can obtain the energy of the system from that wave function. But we can get the good wave function better and better. This is the solution point, yeah, that we can consider, yeah, and the variation process can be helpful to find the better and better wave function. When you get the better wave function, you will get the better energy. Okay, this is the solving of the Schrödinger equation based on Hartree-Fock equation. Yeah. And I have to mention to you a little bit that for the Hartree-Fock, it is the central field approximation. This is the important keyword, central field approximation. What does it mean? It means that the potential that we are dealing with, okay, actually we consider one electron between other electrons. You imagine you have the electron 1 and surrounding by other electrons in the molecules. Okay, so the potential of one electron, that means it interacts with other n-1 electron. And the potential that we obtain is just the average. Okay, this is called central field approximation. I need to mention to you this keyword because when we study on the density functional theory, the concept is different. Yeah, I will mention this later. But for Hartree-Fock, it is central force or central field approximation, as I explained to you here. Yeah, and this is the integral term electron-electron interaction. Yeah, one electron interact with other electron, right? But other electron means that it is the average interaction with n-1, the rest of the electron system. So then there will be several integral terms. Don't worry about that. Just look, okay? Just to give you a little bit feeling that we need to get the operator and the wave function. And to solve this, we need the integral to solve the problem, okay? And therefore, you can see that this means the exchange operator. Yeah? And another term, probably we can consider this term, very similar one, and the integral term over here, it is the Coulomb operator, right? So the keyword is that the exchange operator and the Coulomb operator. Don't worry. I don't want you to remember everything. Just see that in computational calculation, we need to solve this integral, many of them, and that makes the computation takes a long time. Okay, if you can have a high performance computer, you can solve it faster. But if we have not so high performance computer, it takes quite a long time. That means ab initio is just very limited to atomistic system, not much atomistic system, okay, like 10 or 20 atom only. This is the main problem of the limitation of the Hartree fog. And another one, don't worry, just show to you, yeah, about the centrifugal approximation, right? So we have so many terms over here and apply the centrifuges and then generate many terms. But anyway, we can represent some terms like this. If you remember, it's quite similar to Hartree, Hamiltonian operator, yeah. So we call it fog operator. Okay, and this one is the wave function. Don't worry about it. Yeah, I just try to introduce. As I said, you can feel how complicated of the system. Yeah, and the variation method also apply. The variational principle also apply to Hartree fog, and for sure, after the life of many terms, we need to introduce the centrifugal approximation, yeah, in the Hartree fog. And finally, after considering the development of the Hartree fog, and at the end, we can obtain the optimal molecular orbitals that minimize the energy, okay, because we try to get the wave function that represent the molecules at the lowest energy, because the lowest energy is the representing of the real system, okay. The ground state, for example, you need the system that have the lowest energy, right? So in the solving of the Schrödinger equation, the wave function should represent the wave function or the molecular orbitals that produce the minimal energy. And the Schrödinger equation right now, from h per psi of electronic wave function to energy and psi, okay? E per psi equal E, h per psi equal to E per psi. At the end, it transforms to be Hartree fog. This is the fog operator and wave function and eigenvalue and the wave function. Okay. From Hartree fog equation, there are so many criteria that concern about how to explain the system, okay? And also one keyword that I would like to introduce to you is the Protons equation. And the Proton equation consider for the restricted closed shell systems. That means the outer orbital or the valence shell orbital will occupy by 2 electrons. Okay, we call it closed shell system. And for spatial orbitals, you may remember about the alpha and beta, yeah, spin up, spin down, something, and normalized wave function. We have the spin coordinate, yeah, which spin coordinates can be integrated out. So at the end, the Hartree fog equation can be written in terms of only the spatial orbital, yeah, and the spatial orbital means the coordinate of the electron, not include spin, yeah, spin was taken out. There are so many equations over here. At the end, you can see that, yeah, just give you a little bit idea that when Hartree fog and the Proton hole consider step and try to solve the Schrödinger equation, and finally we obtain the Proton hole equation. yeah, as shown to you in the block. Yeah, you can see that this is not easy. Even 1 or 2 atomistic system. From the Hartree-Fock equation, there are still many steps, yeah, to solve the problem. We need to consider electrons that occupy overall space, especially the electron we cannot represent by the Laplacian operator anymore. We need to use the overall space and we need the integral term. Okay. So finally, we have the definition of many things, but still you can see the eigenvalue equation still here. Fock operator and the coefficient, the eigenvalue and some kind of overlap integral and the coefficient, right? So these are the steps in Hartree-Fock try to solve this kind of terms. So I will not make you unhappy by introduce more than this, right? But yeah, try to see the development of the Fock operator that include some kind of still Hamiltonian operator and some kind of the 2 electron integral. Actually, these are the electron interaction, yeah, which is the time consuming. This is the 1 electron term, and this one is the 2 electron interactions. Okay, so we finally, for the Hartree-Fock Rotan-Hall equation, we will deal with the terms that represent the 1 electron integral. Okay, and another term is the 2 electron integral or 2 electron interactions. If you remember, I will remind you a little bit to the here. Remind you a little bit on this slide. You can see that at the beginning, Hartree-Fock Hamiltonian operator consists of 1 electron term and 2 electron interaction term. Okay, and at the end, when we try to solve this kind of problem, so then we face the many of mathematical term, yeah, integral term, but the concept is that at the end you can have the 1 electron integral term and 2 electron integral terms. So to make you a little bit more easier, I like to show this slide to you. Sorry that I have to reduce it and expansion again. That this is the still eigenvalue equation, yeah, or the Schrödinger equation, or later on we call it Rotan-Hall equation. This is the Fock operator. Sometimes we call it Hartree-Fock, right? Hartree and Fock, okay. And actually it is the K multiply K square matrix, okay, square matrix, and consists of the coefficient. And for the right hand side, it is the overlap integral term and the coefficient term, and this one is the sorry, I cannot see it, the diagonal matrix of orbital energy epsilon I, right? Even we write it down in this way, but if you look, it's still the eigenvalue equation, right? And for more easier, we transform this equation to FC equal CE. And in this way, the numerical method will help to guess the coefficient. This is the coefficient, and the matrix. It is a matrix, right? Try to solve to get the coefficient, and then try to find the guess wave function and try to use that wave function to get the energy eigenvalue. Yeah, we can do it. Transform Proton equation by apply the self-consistent field procedure. Okay, the self-consistent field procedure, what does it mean? So we can consider starting geometry, okay, that represented by the coordinate, whatever, and the charge, okay, number of the electron and the multiplicity of the system, for example. And then we guess the initial terms and calculate the orbital, the overlap integral between the interaction between the electron in the mu orbital and the nu orbital. Okay, and then we can find the guess P mu nu, which is the term in also the Hartree. And finally, try to calculate the two electron integral. This is the step, right? The step. Calculate the two electron integral and construct the new Fock matrix. And we can also solve diagonalize the Fock matrix in order to generate the new set of coefficient, yeah, and also the energy matrix. And finally, we can get the new P. Okay, and check for the convergence. I mean, check for the convergence, the criteria. For example, we need to get the energy of 0.0001 or something, right? If it reach that criteria, then we can stop, okay? But if not, we have to come back to the construction of the Fock operator or Fock matrix again, okay? And you can see that this is a very time consuming. Sometimes we generate the two electron integrals, and then we have to put it in the hard disk. Many terms store it, okay, and we can use it later on, okay, to save the time consuming on these steps. Okay, it helps. We call it conventional SCF, or yeah. Or another way, we can, if it's not convergent to our criteria, the energy not reach our minimum energy, then we have to go back and we can use the direct SCF, make it again, or we can use the conventional SCF to save the time. Okay, these are time consuming, yeah. And it deals with the high performance computers that we have. If we have so many big and fast computers, we can solve this process very, very fast. But if not, our systems so big, so many electrons in the molecules, yeah, you can imagine that these steps are really time consuming to get the convergence of the energy, right? So the SCF procedure is important to understand the process, just a concept. In practice, don't worry, computers, programming package will make it for you. So now when I talk to you about the restricted Hartree, we use it as the restricted Hartree or RHF. Yeah, we use it for the closed shell system. The closed shell system means the electron in the outer in the outer orbital, there are two electrons that stay together, spin up and one spin down. And so we can use it like this, yeah, restricted Hartree Fock. Yeah. And the terms, the integral term can be, the spin term can be generated. And for the unrestricted Hartree Fock, like UHF, or we call it the open shell system, that means the outer two electrons not stay together. It can be one choice that there are different orbital, okay, and very active, yeah. These two electrons are active and they are trying to make some chemical reaction occur, okay, or in some case, it can be spin down. And in this case, you can see that the term spin contamination have to be included. Okay, you have the alpha, psi alpha, that means spin up. You can have the spin orbital like this. Or if you have some spin down, you need to generate the psi beta spin down orbital. Okay, this is a feeling, yeah, give you some feeling about the wave function, how to solve the Schrödinger equation, and some representation of the real system. Okay. So for the Hartree Fock method, in summary, I mean mathematical summary, you can have the matrix of the coefficient and matrix of the Fock metric, and then you can have the spin orbital, overlap integral between the two orbital, mu and nu. There are two different orbital. You can have the overlap integral. And you also have the density matrix, which is represented by the P, big P, okay? The big P come from the Fock matrix and Hamiltonian matrix, and some of the term representing the two electron integral. And the P over here is the matrix that consists of the two coefficient matrix, right? Density matrix. At the end, when you apply ab initio to the system, you can get the density matrix that you can use it to calculate about the electron density. Okay, so the molecules, you have oxygen, you have nitrogen, you can see that the electron density are different. Okay, and how to know it, yeah, you have to use the density metric. So the resultant solution is then the matrix equation that we call it Hartree-Fock-Rotan equation here, this one. Hartree-Fock, Hartree products, that means Slater determinant and then Hartree products and Fock operator to help solving the Schrödinger equation, and also the SCF procedure, and also the central field, and also many techniques that I have introduced to you a little bit. Overall, we call this equation like Hartree-Fock-Rotan equation, which is very famous, okay, in ab initio. So you can see that within this equation, it consists of the overlap integral, it consists of the density matrix, and also it consists of the Fock matrix, right? Yeah, these are terms that atomistic basis space. Again, for the self-consistent field procedure, yeah, it is very important by apply this SCF, we call it SCF procedure, to solve the Hartree-Fock-Rotan equation. Yeah, as I introduced to you, we start from the trial solution, okay? Build the Fock matrix, and then diagonalize it to find the eigenfunction to start the next iteration. Yeah, like the cycle. The first cycle is just trial, anything. But after get the eigen function, we start the second cycle and third cycle and fourth cycle and so on. Okay, this process will keep going until the energy and or the density difference between the two steps are less than the certain criteria. For example, we expect to get the lowest energy before the last step, and the last step energy should not different than something. Okay, we have to fix that, and then it will stop. So this is the self-consistent field procedure that in the ab initio they will do this, right? Choose the start coefficient for molecular orbitals, construct the Fock matrix with the coefficients, and solve Hartree-Fock-Rotan equation. Okay, and get the eigen functions. That means the energy. Okay, and repeat the second term and the third term until it outgoing get the criteria. Yeah. Then, and these are the time consuming in ab initio. So just put to you in this picture to see, yeah, to see what is the Hartree-Fock is. What I have introduced to you this morning is the how to consider how to solve the Schrödinger equation based on the Hartree-Fock, yeah, and apply the SCF. And at the end, we have the Rotan-Hall equation, Hartree-Fock-Rotan-Hall equation. It is the main ab initio. But after Hartree-Fock, okay, we need to study about perturbation, hierarchy, MP method, and so on. And also we need to study on the excitation, which the method like CIS has to be introduced. And if we like to get the best prediction from ab initio, yeah, we need to apply the full configuration interactions. Okay, and yeah, if you are interested in, we can do it. And these are the whole picture of Hartree-Fock based method. Yeah, it means we have Schrödinger equation. You remember that we introduced this. Okay, one electron terms and the two electron term. Okay, operate on the wave function, and then we get the energy eigenvalue and the same function. And for the wave function, we starting by apply the Slater Determinant to help. Okay, in order to obey the Pauli exclusive principle and anti-symmetric condition. So Slater can help. Okay, so we have the wave function of the Slater wave function. This is the Hartree-Fock theory. And later on, we apply the centrifugal approximation and variational principle. Okay, as you remember about the self-consistent field SCF, and we obtain the Fock equation F per psi equal E per psi, right? And these are the Hartree-Fock, right? And after Hartree-Fock, it is these are the new method that we have to study next week about the MP, CI, and the couple cluster method. Okay, so interesting for this picture. Yeah. So for this lecture, at the summary of the Hartree-Fock method or the ab initio, the main ab initio, the one fundamental on the ground state wave function. Yeah, we approximate the quantum mechanical method by starting of all ab initio calculations by applying variational theory, yeah, in order to get the energy at the Hartree Fock, yeah, into the real. And we apply the cell consistent field theory in order to help to solve the equation. The scale of the number of the basis function can imagine, if you have the basis function, you imagine that you learned last time about the basis set, you may have 10 or 20 or something, and then you have to power to 4, right? And Hartree proposed iterative cell-consistent field method. Yeah, the very important step is that guess the wave function just to construct the one electron operators, and then later on solve to obtain the new wave function, and make this cycle predict about the coefficient and the eigenvalue until we obtain the wave function that make the convergence and reach the criteria that we would like to have. Okay, for the Fock operator, we extend the SCF to include the electron exchange effect to the Slater determinants, right? But these are a little bit more into details. So the approximation in Hartree-Fock theory, right? You remember that we have the major approximation. I would like to say that in ab initio, actually there are so many approximations, but those major is Born-Oppenheimer. Yeah, you remember that we apply to the Hamiltonian operator approximation and also the wave function approximation based on this big elephant and the fly, right? And neglect relativistic effects. Yeah, the solution is obtainable from the linear combination of finite basis functions. The energy eigenfunction is described by single Slater determinant and also mean field approximation. Yeah, is replaced for all interactions of the electron in the system, as I mentioned to you, the mean field approximation. And the procedure of the Hartree-Fock and SCF, as I said, is very easy to understand. Choose the basis set, choose molecular geometry, guess initial density matrix, construct and solve Hartree-Fock equation, construct the new density matrix, and then new density matrix sufficient similar to the old one. If not, repeat the new density matrix again and again until it reaches the criteria that we would like to accept. Yeah, or if we need optimization geometry again, we can optimize and then acceptable, yes. If not, we have to choose geometry and come to the iteration again. Okay, so these are the computation, these are the computational calculations that deal with the ab initio. And the Hartree-Fock SCF procedure is there, very helpful. Okay, now I think we can learn a little bit about every method that I mentioned. They are good, right? But there are some limitations. And the strength of the Hartree-Fock is that Hartree-Fock limit result is the upper bound of the true energy for the system. Yeah, sometimes how to say, the prediction on the energy of the molecule sometimes is not correct or not close to the real system. Okay, it might probably higher or something. And acceptable result of minimum energy structures. Yeah, this is very, very good. If we try to optimize the conformation for the minimum energy, Hartree-Fock is good. And we can use double zeta polarized basis set. Last week we studied about the polarized basis set, okay, and resulting in some error for sure, but in the very small error like 0.03 angstrom, or error in heavy atom hydrogen bond length, very small angstrom, and error in bond angle about 1.5 angstrom degree, sorry, and dihedral angle are generally good. Hydrogen bond are generally good. Okay. However, there are some weaknesses, right? For example, in Hartree theory, the bond interactions tend to be overestimated, and the bond lengths are usually too short as compared to the real structure. And there are some failure to account for electron correlation. Therefore, the Hartree should not be used for reaction energies, but potential energy is fine, okay? And should not be used for structure with the dispersion. Yeah? Like the structure that have so dispersed energy, like aromatic system, okay? And the heavier atom prediction lack inclusion of relativistic effects, this for sure, because it neglect at the beginning. And the unoccupied orbitals are not optimized, right? You may imagine there are some unoccupied orbitals, and in the Hartree it is not dealt with. So you can see that based on this weakness, that means the method to solve the Schrödinger equation have been still developing. The Hartree after Hartree there are so many methods that, as I told to you, right? So if we have the number of atoms about 10, we can use the Hartree right? Local density Hartree over here about 100. But if more than that, it is not possible. And if very small number of atoms, then we can high up the accuracy based on the other method, after Hartree method, right? I have some example, just a couple of example that accuracy of Hartree calculation are quite nice, like Hartree wave function recovery 99% of total electronic energy, and some details on this kind of details. And for example, if you consider the CO, yeah, the spectroscopic constant of the carbonyl CO, you can see that for the Hartree prediction of the equilibrium distance between the CO is 1.1 and experimental is 1.13, right? Quite nice, right? And some dissociation energy also some difference anyway. And in terms of enthalpy change or the delta H in kJ per mole from many of the chemical system like methane and so on, you can see that enthalpy change as compared to the experimental, right? There are so many methods like the couple cluster predict quite nice. You can see that, yeah, for the first reaction and also for others. And for the SEF, Hartree SEF itself not so good. And this one is the Gaussian, the program package. Use MP2 and the DFT. Okay, DFT quite nice also. Yeah, this just give you some feeling about the properties of the reaction like enthalpy. Yeah, we can do it based on many methods. So I think we come from almost the end of my lecture. And today I have introduced to you about the ab initio method. So please just try to learning and try to summarize something. What is the ab initio method? Okay. and how many approximations in the ab initio method is very important to know. There are so many approximations that means it cannot how to say, represent the real system at the end, right? The computation, but from some system, you can see, as I told you, as compared to the experimental, yeah, ab initio can predict quite well, but some system not, yeah. And probably you can explain the strength and the weakness of the Hartree fork. And this is the practice every time I teach my students, every method that we use. The student should know the tools or the method that you are using. If it fit to some system, or if it cannot apply to some system. Yeah, this is the way that you can understand the method, and you can select the method for yourself, for your system. You know about the strength, the weakness, okay? You know about the limitation. Yeah, this is the way of computational chemistry practice. All computational chemists, they have to know about their method. Yeah, and if so, you can calculate, you can predict, you can model everything with the appropriate results. So we can come to the question and answer, I think, and further reading, also many things available for you if you are interested in. And I do hope that next week we can continue about the post-Hartree fork method. Yeah. So that should be all from me. Okay, and I have seen the question, right?
Yes,
the question, the second question. สวัสดีค่ะอาจารย์ สวัสดีค่ะ So you know about Thai greeting. Winnie, Effia.
I think
Thank you.
she is one of your husband's student.
Oh, really? Oh my God.
Yeah, I believe so.
I will tell my husband, Ajahn Supot. Yeah. So Winnie.
Yes, actually, I'm from Chulalongkorn, Achan.
Yes.
But I haven't met Achan Support yet.
Okay, you know one Ajahn, right?
Yes.
Yeah. Okay, your question is that in Hartree fork theory, indeed, there are the RHF and UHF, but there is the third one of Hartree fork, that is ROHF, restricted open HF. Do you mind to elaborate more about the ROHF and the chemical system that we usually apply the ROHF, please? Restricted open HF. Oh, actually, I myself, I'm not familiar with this. Okay, but if you don't mind, I may try to answer your question next week, Winnie. Yeah.
Yes, Achan.
Because I think it's quite special case. Not
Yes,
general
okay,
case.
it's okay.
Yeah. Okay. Why do you interested in the ROHF? Do you apply it yourself, or just like to know?
I understand about the RHF and unrestricted HF, but I still didn't understand about the ROHF.
Okay.
And at least in the concepts, I still unclear with it.
Okay. Very good. So I will come back to you next time, okay, about this question, because I am not familiar, but I think I can find your answer and correct answer to you. Is that okay?
Yes,
Winnie?
Yes.
Thank you. And how about you now? You already graduate or still studying?
I'm still I'm the first year in physical chemistry division in master program.
You are the academic staff, not the student, right?
I'm a student.
Oh, you are a student, master degree student.
Yes, first
Okay.
year.
Okay, very good. So you know many things already about Hartree. Very good.
Not very much, but yeah,
Yes,
I'm familiar
maybe.
with.
That's nice. That's nice to see you. And which university that you are studying now?
It's Chulalongkorn.
Chulalongkorn. So now you are in Indonesia or in Thailand?
I'm still in Indonesia, but I'm planning to come to Bangkok in next couple months.
Okay, so I hope that I can meet you. And I also I also welcome the student Nakamita. I also welcome the student from you from Indonesia. If you like to visit Bangkok, Start University or Chulalongkorn University, or would like to have the short-term research, yeah, I'm sure that we can welcome you all. Just let me know.
Well, thank you very much. You can
Thank you.
Thank you, Prof.
Yes.
And
I think it's quite tough topic today. If you like to give some feedback, I mean, if you like to know some examples or what kind of thing that the student can understand more, yeah, you can feedback to me, and I myself next time about the post Hartree, I will try to show the example of the chemical reaction or case study. Yeah, that would be more nicer and enjoyable.
Yeah, thank you very much, Prof, for the explanations. I do believe that all of the participants here are still hungry about the computational chemistry applications. And finally, now we have learned about how computational chemistry works, and it is not only you put something in your computer and then you get the results, but you make the control of all of the calculations. You have to choose where is the best one, what is the best method for your systems, and you also have to know your system very well. And finally, we know that what we learned about Schrödinger equations in our previous course, maybe, and now it is the use of Schrödinger equations. We employ the Schrödinger equations to describe our system, to get the information about the energy and so on. Thank you very much, Prof, for a kind lecture today.
Yes.
See you on the next meeting.
Yes. Okay. See you next time.
Yeah, thank you very much, Prof. And
take care, everybody.
Take care, Prof.
Take care, Professor.
Thank you.
Bye. Thank you.
Have a nice day.
You too.
Thank
Thank
you,
you,
Prof.
everybody. Take care.